Hello everyone. So today we will be discussing about classical versus quantum computing. Classical computing is the foundation of modern digital world. It's responsible for many technological advancements we use today. These computers process information using bits, which are binary units that can be represented either a 0 or a 1. Every task a classical computer performs, from basic calculation to running a complex algorithm, involves manipulating these bits through logical operations. In contrast, quantum computing takes a completely different approach, using the principles of quantum mechanics to process information. Instead of bits, quantum computers uses quantum bits. They are also known as qubits. Unlike classical bits that can only exist in one state at a time, either a 0 or a 1, qubits can exist in the state known as superposition. This means that a qubit can represent both 0 and 1 simultaneously. We will dive deeper into this particular idea later. But for now, understand that the property allows a quantum computer to process vast amount of information at once. And this particular property is known as superposition. Now, why does this matter? The ability to perform many calculations simultaneously gives quantum computer a huge advantage in solving certain types of problems which are much faster than classical computers. Here is an example that illustrates the difference. Imagine we are trying to simulate a complex molecule like caffeine molecule. It has 24 atoms. To represent all the quantum state of this molecule, a classical computer would require an astronomical number of bits 2 raised to power 160, which is an unimaginably large number. On the other hand, a quantum computer could do this task in just 160 qubits. Now consider even a larger molecule, penicillin molecule, which has 41 atoms. Simulating this molecule's behavior would demand 2 raised to power 286 classical bit. That put that in perspective, this is more than the number of atoms in the observable universe. Yet, a quantum computer could perform this task using only 286 qubit. This example highlights the extraordinary power of quantum parallelism, the ability of quantum computer to explore multiple possibilities at once. Quantum computing isn't just useful for simulating molecules, it's also incredibly powerful for solving optimization problem. Take the traveling salesman or TSP as an example. This problem involves finding the shortest route for a salesman to visit a number of cities and return to the starting point. As the number of cities increases, the number of possible routes grow exponentially. For just 100 cities, there are 9.3 quintillion possible routes to evaluate a number far beyond the reach of classical computers. A quantum computer, however, can evaluate many possible routes simultaneously, offering faster and more efficient solution to such optimization problem. So here are some key differences between classical computer and quantum computing. If we see in terms of basic unit, classical computing use bits which is 0 and 1, whereas quantum computing use qubits which is 0, 1 or both simultaneously in superposition. State representation in classical we have single state at a time, whereas in quantum superposition qubits exist multiple states at a time. Classical computing use sequential processing, that is step by step, whereas quantum computing uses parallel processing where we can have multiple calculations simultaneously. Classical computing uses Boolean logic and or not, whereas in quantum computing we are having quantum logic gates such as Hadamard gate or C0 gate, etc. Classical computer stores the data in binary format, whereas quantum computing stores the data as a quantum states. In terms of computational power, classical computer is limited to power of processor, which will increase linearly with the resources, whereas in quantum computing it scales exponentially with the number of qubits. In terms of error tolerance, classical computer are relatively low error rates with error correction through hardware and software, whereas in quantum computing it has a high error rate and it requires complex quantum error correction. In terms of optimization problem, classical computer solves via exhaustive or heuristic search, whereas quantum computing solves this using possibilities, evaluating various possibilities simultaneously. In terms of encryption, classical computer uses traditional cryptographic algorithms such as RSA, AES, etc. Whereas quantum computing breaks the traditional encryption, but it enables quantum safe encryption. In terms of simulation capabilities, classical is limited to simple model or approximation, whereas we can simulate complex quantum system accurately in terms of quantum computing. In terms of energy efficiency, it consumes more energy as the computational complexity increases, whereas in quantum computing, potentially more energy efficient for specific tasks. In terms of physical requirements, classical computers still using transistors, chips, and electricity, whereas in quantum, we require highly specialized hardware, cryogenic temperatures, which is really, really cool, and quantum gates. Despite its incredible potential, quantum computing is not a one size fits all solution. There are significant challenges to overcome. Building a stabilizing qubit is one of them. Qubits are highly sensitive to their environment and can easily lose their quantum state due to disturbance. This requires precise control and advanced technique to stabilize them. Another is error correction. Quantum computations are prone to error. So scientists need sophisticated error correction method to ensure accurate results. And one more is specialized use cases. Here quantum computer excel at specific type of problems like optimization problem or simulations, but they won't replace classical computers for general purpose task. So that's all for this particular video. We will be coming up with more informative videos regarding quantum. Till then, like, share, and subscribe.